Hello, everybody. It is a big pleasure to have today a talk by Steve Giddings from Santa Barbara. He will tell us about black holes and information and update. Please, Stephen, 1 hour, but this is up to you. And maybe I can ask you first a question. What do you think? People, can you interrupt you during your talk, or you prefer to collect all questions after the end? What is your decision? Tell us.
I think there is some time that we have for questions. So I think some questions could be asked during the talk, as long as we don't get too far off track or too far behind. So that's okay. Fine. I encourage some questions. Yeah.
Okay. Thank you. Okay, please start 1 hour. Mm-hmm.
Okay. Thank you, Irina. And thanks to all of the organizers for the opportunity to speak at this very interesting ongoing series. Hello, everyone. And like was just said, to a point, we can encourage questions as long as I can keep things on track. So the problem of black hole information is something that I've long believed is, and I think many others have evolved to varying degrees to this viewpoint, that I've long believed is a key problem for quantum gravity, much as understanding the atom played a key role in the development of quantum mechanics. Now, if that is the case, we would clearly like to be able to use it as a guide to the new principle of...
yes, this is just, yes, the recording.
Should I restart with the recording? Or,
yes, it's okay.
Okay, so so if the problem of black hole information is indeed such a key problem, we would like to use it as a guide to understanding the principles of quantum gravity. Or even more intriguingly, possibly, since black holes have entered the realm of observation, this problem could lead to new observational signatures of quantum gravity, which would be very important indeed. So today, I'd just like to give some updated perspectives on this set of questions. And of course, there are various perspectives on the problem, as well as proposed resolutions. For example, there has been a lot of focus in just the past couple of years on entropy calculations in particular, but it's worth emphasizing that entropies are just one diagnostic of what's going on, and there's more to be understood. And so what I'll start out with today is a suggested way to organize our understanding of the problem, which connects to the information theoretic perspective and focuses on certain questions that may be important in terms of understanding, say, the structure of quantum gravity and so on. So in fact, I'm going to organize things around what I'll call a black hole theorem. I very much put this in quotes. One of the reasons it's in quotes is I view this as a statement that is in a similar spirit to the Coleman-Mandula theorem. Of course, the most interesting part of the Coleman-Mandula theorem was the little loophole in the theorem through which supersymmetry snuck. And so that led us to something truly profound and important. The discovery of supersymmetry ultimately was related to that loophole. And so when I say black hole theorem, again, an interesting thing to focus on is, where does the loophole lie? That's where the really interesting physics probably is with regard to quantum gravity. So what's the statement of the theorem? So the statement is, if a black hole is a subsystem and distinct black hole states, so if a black hole is a subsystem, it can have distinct, say, internal states. If distinct black hole states have identical exterior evolution, and if a black hole disappears at the end of evolution, then this violates quantum mechanics, specifically unitary evolution. So this is a set of statements that could also be made in application to other systems, but we'll focus on the context of black holes. And probably the first thing that's important to do is to clarify what is meant by these various assumptions. So I'll go through them one by one. So a black hole is a subsystem. So colloquially, in a lot of the literature, this is stated just by, say, representing the Hilbert space corresponding to the universe as a product of a black hole Hilbert space and an environment Hilbert space. But that's not quite the right way of thinking about things. For example, in the context of local quantum field theory, at least such factorizations can be a little problematic. So let's be a little more careful. And so first I've drawn here two diagrams representing the space-time of a black hole. Many people prefer Penrose diagrams, but I'm going to actually focus more on Eddington-Finkelstein pictures because it removes some of the distortion up in this little corner where a lot of the interesting stuff is happening. But one way or another, those are black hole spacetimes. And I've drawn in green here slices through those, spatial slices through those spacetimes. And we can think about the state of the fields on such a slice. And so let's describe what we mean by a subsystem in that context, the context of local quantum field theory on a slice. And one way of putting it is there are separate attributes of the state that correspond to excitations inside the black hole or outside in the environment. So you can write the state that way. Or if you don't want to make such a sharp division at the horizon, you might want to include, say, an atmosphere subsystem that acts as a buffer in between, although we won't really need that for today. So that's one way to think about what a subsystem is. Another way in which subsystems tend to be precisely formulated in quantum field theory is in terms of commuting operator subalgebras. The observables that correspond to observations outside the black hole, observables supported outside the black hole, commute with the observables inside the black hole. You have commuting subalgebras of those two sets of observables. Yet another way of thinking about subsystems is in terms of, say, the split vacuum, but I won't go into that construction today. So at least at the outset, in the framework of local quantum field theory, that's what we mean by a subsystem. And one point I want to make at this stage is that in local quantum field theory, or when talking about other quantum systems that we explore in nature, the subsystem structure really is fundamental. It's hardwired at the beginning as one of the starting points of the physics discussion. Okay, second. Here we go. The second statement was that distinct black hole states have identical exterior evolution. So let's consider evolution along a set of spatial slices like I've drawn, these slices in green. And so we've discussed the representation of the state with, say, interior and exterior degrees of freedom or excitations. And if we consider different internal states of the black hole, say where I have one or another excitation, then by the statement that in field theory we evolve within the light cone, the influence of those different states is restricted to this region between these two light trajectories, which I've drawn. Here's the, so to speak, ingoing and what would be the outgoing light trajectory, but of course that goes into R equals 0. And so that means that the behavior of the state outside the horizon doesn't depend on what excitation you might have on the slice in this particular region. Okay, so in local quantum field theory, as described a la Hawking and so on, you have unitary evolution from slice to slice that has this property that the evolution of the external part of the state is independent of the internal degrees of freedom, so to speak, or the internal part of the state here. So we can see that very concretely. We can write down the unitary evolution operator from local quantum field theory that corresponds to Hawking evolution. In at least a couple of recent works, I've been trying to write down more carefully how all this works in this kind of Schrodinger-like picture. And then with a Santa Barbara student, we're extending some of the two-dimensional story to higher dimensions, again, in a Schrodinger-like picture like this. But anyway, that's something that's very concrete. Now, to characterize this independence of the outside, you can describe things in various ways. One thing that is commonly done is to formulate a density matrix, which is gotten by tracing over the internal degrees of freedom of the black hole. And so that is something that should be independent of the part of the initial state here that is inside the black hole, in the black hole subsystem, so to speak. Though formulating such density matrices is a little bit problematic because you run into issues of cutoff dependence and how to precisely state what you mean by taking the trace, and that becomes even more important, I think, once you include gravitational effects as well. Another way of saying what this independence means is that the identical exterior evolution is if you look at observables outside the black hole and look at how they evolve in the evolving state, that the expectation value of those observables will be independent of the part of the state in the black hole subsystem on the initial slice for all exterior observables. And of course, this property of identical exterior evolution follows in the local quantum field theory description precisely from the property of locality, at least formulated in terms of the statement of observables commuting outside the light cone. Now, one thing I've done here is I've ignored the gravitational back reaction, but one can do a little bit better and include that as a semi-classical correction to the evolving geometry, like we did way back with the the CGHS work with two-dimensional black holes. So one can even improve on this somewhat. Okay, finally, a black hole disappears at the end of evolution. So we have our internal part of the state and external part of the state. And what this means is the evolution operator, whatever it is, if the black hole disappears, should map you to a unique state. You might think of it as the vacuum or some particular, well, in some other basis, some black hole final state. But there is no longer any degree. There are no longer any degrees of freedom here. The black hole has disappeared, and you have just the state of the environment, and that's independent of the initial, say, internal states of the black hole. And here's where we find the statement or the truth of the theorem. In fact, it's kind of trivial, because if this is what happens, then you have evolution that is many to one. And so whatever this evolution operator is, it must be non-unitary, and thereby it violates quantum mechanics. There are various ways of diagnosing that. You can think about, say, taking the initial state and entangling it with an auxiliary system, for example, and then you have non-zero entanglement entropy between your auxiliary system and the state of the black hole plus environment. And then, of course, if the evolution is such that it forgets the black hole state like this, then in the final state, the entanglement entropy would be zero. And so that's one way of stating how you're violating quantum mechanical evolution. There are different ways of doing it. And of course, this auxiliary system you could think of as even the early Hawking radiation, which do have an entangled structure with the internal degrees of freedom of the black hole. Okay, so that's the simple set of statements that lead to a contradiction with quantum mechanics. And to evade this problem in rescue quantum mechanics, clearly we need to violate one or more assumption. And so like, as I mentioned, with Coleman-Mandula, the loophole could be the most interesting part and may guide new principles. There are, of course, various proposed outs to escapes from this chain of logic. And a good test question is, how does your favorite proposal, whatever it is, differ from local quantum field theory or Hawking, specifically Hawking evolution, particularly with regard to this set of statements. And of course, as I said, we have an increasingly detailed story about how Hawking evolution works. And so we can try to understand, where really are we departing from that? So let's go down a list of some of the things that have been talked about in the past. One is the original suggestion that maybe a black hole leaves behind a microscopic, say, Planck scale remnant. So this would, of course, violate the third assumption on my list, that the black hole disappears at the end. You'd have something left behind containing the information or the degrees of freedom corresponding to the black hole interior. And so that's how one evades the statements I've made. But of course, as we know, that kind of scenario introduces other rather severe problems, basically infinite production of those remnants. And that's something I'm not going to discuss here, but at least there's some discussion, for example, in these papers of the trouble with that scenario. Another idea is that a black hole at some stage, maybe early in its evaporation or later on, transitions into a different kind of object that has, say, extra degrees of freedom in place of the horizon. We could just call this generically a massive remnant. So this happens while the black hole is still quite big as compared to the Planck scale. And there are multiple examples of this kind of scenario that have been discussed in the literature. Of course, fuzzballs fall into this general category, firewalls, gravastars, Planck stars, and so on. There are a number. And where that would depart from these assumptions is, of course, you're changing this structure of subsystems. You don't have a sort of independent subsystem corresponding to the black hole interior. It's a different structure. And of course, it's a big departure from the evolution predicted by just local quantum field theory. Another scenario is the one that Gerard Atouf talked about at the first talk in this series. And I'll leave it to him or as an exercise for one of you to explain where that differs from the Hawking story in this way of looking at things. And likewise, for example, there's been a lot of discussion of ER equals EPR. And so you might think of that as basically involving a different subsystem identification, although I've always found it a little bit hard to understand, at least systematically, how that works. So it would be nice to have some systematic explanation of that a little more in this kind of language. And then, of course, recently, replica wormholes have been explored quite a lot and have been of real interest. Here are just a few of the recent references. Of course, there are many more. I can only give the most prominent ones here. But the basic idea is, say, if you look at the entropy, we have the growing entropy of entanglement between the outgoing radiation and the black hole degrees of freedom. And then we have another curve, which is the decreasing area or Bekenstein-Hawking entropy of the black hole. And we believe that what should happen if the black hole is going to basically respect quantum mechanics is that the entropy, the actual entropy of entanglement should follow a curve something like this. It should follow this sort of composite curve where you go up for a while and then you come back down. That was explained to us, for example, by Page quite some time ago. And so the question is, if you look at just the diagnostic of the entropy, how do you explain this? And so the recent Replica wormhole story has given a proposed explanation for why you reproduce these known entropy curves by essentially giving a prescription that involves taking different saddles that are thought to dominate in the two different regimes. And the prescription for basically taking those two different saddles then reproduces this behavior. But one of the questions in this, at least in my mind, I think in others, is how do we relate this story to the standard quantum mechanical language of states and amplitudes? Or does it even represent, say, a modification of quantum mechanical rules when you sort of formally sum over all replica geometries? So it would be nice to have some more clarity on this. We've given some discussion of these issues, a number of others have as well. The closest thing to a story matching on to the usual story of sort of states and amplitudes is this connection to the idea of baby universe emission. So replica wormholes are in some ways similar to space-time wormholes, which can represent the process of emission of a baby universe. So the picture that you might have in mind is something like this. You have a black hole interior and horizon, and in some sense that undergoes a transition where you emit some separate piece of space, which you might call a baby universe. So of course, Merolf and Maxfield have really explored this kind of picture, as have others. And so there's a question of whether this way of thinking about things explains what's going on. So first of all, it seems like that when you look at the way I frame things in terms of the different assumptions, it seems like that's a modification of the subsystem structure. You've got extra degrees of freedom, an extra Hilbert space of your baby universes, and it looks like in some sense the information from the black hole interior can be going into the baby universe Hilbert space. And so you might think that that's a nice way of explaining ultimately what's going on. But quite some time ago, we looked at similar processes in a slightly different context, and in fact studied the effects of baby universe emission, at least in a certain approximation, basically where you're neglecting interactions between baby universes. This was work back in the 80s of Coleman and myself and Strominger. And in a fairly general way of parametrizing those with a mild set of assumptions, you can summarize the effects of baby universe emission by a correction to the Hamiltonian with the following structure. So it's basically got an annihilation and creation operator for the baby universe. So that acts on the baby universe Hilbert space, times an operator that represents the effect of this emission process on our part of the universe. And with that structure, you see that what you can do is diagonalize this baby universe part of the operator and work in what's called an alpha eigenstate or alpha vacua or alpha vacuum. Here the labels I just might correspond to different internal states of the baby universes. And once you've done that, if you've diagonalized the baby universe part of the Hilbert space in this way, then you see that you just have a correction to the Hamiltonian that some operators acting on our part of the universe times some new effectively coupling constants. So if these operators are localized inside the black hole, or on scale small as compared to the black hole radius, it's hard to see how that helps. Specifically, it's just giving you some new coupling constants, and then you're back into the set of assumptions I outlined in the statement of the black hole theorem. That remains, and there's no clear way out of the underlying logic once you work in one of these alpha vacua. On the other hand, there is a possibility that's interesting here that goes beyond that, and that is if these operators that act on our part of the universe are non-local on scales of order the black hole horizon size or bigger, then clearly you can violate assumption 2, and you can have the outside evolution be dependent on the black hole state. effectively that introduces couplings between the black hole interior and the environment would amount to non-local interactions. And so that would violate this assumption too. That kind of idea is something I will return to. And so that is something to consider. Or it maybe there's some other interpretation of this whole replica wormhole story in this language. Maybe folks on the replica wormhole side will tell me what it is. I'm still trying to figure out what it is from my perspective. So it'd be nice to have an explanation of what is really supposed to be the picture for what's going on with replica wormholes. But let's just back off and return to a more general discussion, going back to these assumptions. And in particular, we could ask the question, how much significantly new structure needs to be introduced? Do we really need such a drastic departure from the expected near horizon geometry as, say, a firewall or a fuzzball or various other things? And so let's go back to these underlying assumptions and look at them a little bit more closely. And the first one is a black hole is a subsystem. And a very good question in the context of gravity in particular is just what is a subsystem? That's a very important basic concept. And as I mentioned, in general, when we think about description of quantum systems, usually we start with some description of what that means. So just as a reminder, for finite or locally finite systems like lattice systems, we think of subsystems in terms of factorization of the Hilbert space. And one of the characteristics that represents, writing the Hilbert space as a product, is basically you can make measurements in this part of the Hilbert space, and they will be independent of the state in this part of the Hilbert space. Of course, you could set up a correlated state, et cetera, to begin with, but there always will be states where you have this statistical independence of the two pieces. Okay, so that's the locally finite or finite story. What about local quantum field theory? Well, there, as I mentioned, it's a little more problematic to just simply factorize the Hilbert space. That's associated with the type 3 property of the von Neumann algebras associated with local quantum field theory. It's better to instead think about the operator algebra and its commuting subalgebras. And you have, say, commuting subalgebras corresponding to different regions, as we've already mentioned. So this is the basic approach of algebraic quantum field theory. It's nicely explained in various pedagogical treatments, like, for example, Hogg's book, and so on. And so one thinks of the, say, decomposition into subsystems in that language in terms of the subalgebras. Let's just give a simple example of what that means in just to illustrate. And so if we think about, say, a scalar field, we can consider a neighborhood here. And let's think about a state of the scalar field theory where we take a compact support function J, think of that as a source, and we integrate that against phi and act with this operator on the vacuum. And of course, as I think pretty much everyone here knows, if you do that, you can't tell the effect outside the neighborhood. So specifically, if you look at, say, the expectation value of the field phi at some space-like separated point here in this state, the expectation value of that operator will be the same as the expectation value in the vacuum. So that's, again, reflecting this property that a measurement outside is independent of the state inside. And that, again, is a basic property that Hawking evolution respects, and that's what constrains the escape of information from black holes, at least if you try to describe that within the local quantum field theory approximation. Actually, I'll stop here and see if there are any questions to this point. As I mentioned, questions are welcome up to a point. Okay.
Oh, There is one question. Please ask your question.
Yes, good morning. If you start off with a star before it's collapsed into a black hole and you've got it coupled to an environment, can you see the subdivision of the two states, namely the product of the black hole times the environment wave function? Because that will answer for you what you mean by a subsystem.
Well, okay, so there are various sort of levels at which you could ask that question. If we're ignoring gravitational effects, then a collapsing gas that's going to form a black hole, say that corresponds to a star, can be thought of as a subsystem that's separate from, say, other degrees of freedom elsewhere, just like in any other quantum systems described within quantum field theory. So at least at that stage, it looks like you do have a labeling of, say, the states of the star versus the states of the exterior. And you might think that that persists once you form a black hole. But of course, there are, and that's what local quantum field theory in essence is telling you if you give a local quantum field theory description of it. But of course, there is the question of gravity, and that's what I'm about to come to.
Okay.
Any other questions? Okay, so I'll go ahead. So, okay, so and on to the interesting question, how do we think about subsystems in the context of gravity? So in gravity, the field operator phi of x, or other fields, is not gauge invariant because the gauge symmetries include, or are diffeomorphisms which move the point x around. And one way of stating that is in a just different language is that the field operator doesn't commute with the constraints. The constraints generate the gauge transformation. Likewise, this kind of localized state that I described is not gauge invariant, and it's not annihilated by the constraints. And specifically the constraints, if you think about describing gravity as an effective theory of basically quantum GR, the constraints look like this. It's basically what you would get if you tried to write, well, put all of Einstein's equations on the right-hand side of the equation and divide by 8 pi g. And of course, consider the 0 mu components of those. Okay, so those are the constraints. They generate the gauge transformations, and these things don't commute with them or are not annihilated by them. And physically, what that's telling us is that a particle is inseparable from its gravitational field. So how do we correctly incorporate this? Well, we can construct solutions to the constraints by basically understanding how things get gravitationally dressed. And we can treat this in a perturbative way by, say, working about a given background and considering the full fluctuating metric as a perturbation on that, where kappa is basically the square root of Newton's constant. And we treat that as the parameter we perturb in. And so in such a perturbative approach, you take, for example, this initial, or this state that I described, just the local quantum field theory state that's localized, and it needs to be promoted to a state now that is annihilated by the constraints. And you can find at least a leading order solution to that condition, that this is gauge invariant, which you get by basically taking this underlying field theory state and acting on it with an exponential of a certain integral of the metric perturbation, which I could give more details on, but you can look that up in these papers. Integrated against the stress tensor, and so that's exponentiated in x on the state. Likewise, for operators, if we want to dress them, we have the commutator, or sorry, the conjugation of the underlying operator by such an operator. And so these papers showed that this is a way of constructing solutions of that condition to leading order, that you basically satisfy the constraints. First done in flat space here, and then also in the anti-de Sitter context in a paper with Kinsella, and then there's been also some recent study of the same thing by Chowdhury et al. So the picture is that we had our localized field theory state here, but of course the operator that, say, creates that state from the vacuum also has to create its gravitational field, gravitational dressing going off to infinity in some way. There are actually different possible choices of that gravitational dressing as well, and that's part of the story that is interesting, but I won't focus a lot on today. But one thing that is very important now is with this gravitational dressing, say if we have two such operators, which we think are space-like separated, well, really, they will no longer commute because basically the gravitational dressings of the two don't commute. And so we no longer have the same kind of locality structure we had before. And this you can check quite explicitly. Or, for example, if you have such an operator and say, look at the expectation value of the metric fluctuation outside the neighborhood, you also are sensitive to the fact that you acted with this operator because the metric fluctuation sees the gravitational dressing. So the story of how subsystems work is obviously modified from the underlying story of quantum field theory. And so this raises a very important question. In what sense does information localize in gravity, and what is a subsystem? In fact, this looks like a key structural question, which we ought to better understand the answer to. So I'll just state some results. First, I said there were choices of the dressing, and the perturbative dressing can be chosen such that, for example, if you look at measuring the perturbation of the gravitational field outside the region, then those expectation values of products only depend on the Poincare charges of the underlying state, and that's something explained in the papers here. That, by the way, suggests a limited role for this whole soft hair story, because basically the soft hair charges correspond to just different choices of the external excitations of the gravitational field or of the gravitational waves, so to speak, in the that are, say, outside the neighborhood. I won't elaborate on that, but at least that's the story with measuring the gravitational field itself. But on the other hand, there are observables, other observables that can see the state from afar. And an example is the following. Actually, the underlying statement that is important is that if you think about the translation generators in gravity, the full translation generators can be written in terms of the ADM expressions for the ADM translation generators, which just involve the metric out at infinity, plus an integral of the constraints. And so that statement tells you that if you have satisfied the constraints, then the translation generators just correspond to expressions that live at infinity. Okay, so this is argued to lead to a way of sort of reading off information at infinity about a state in a region that goes back to Merrill, who discussed this in the context of anti-de Sitter space. And so the basic picture there is consider one of the states that I've discussed, say, where you have an excitation in a neighborhood, and I haven't shown the gravitational dressing, but it's there. And then we can convert or relate the state or an operator here to an operator up, say, on the boundary of anti-de Sitter space by just following propagation, within the light cone. But then once we've related to operators on the boundary through propagation, then we can use the fact that the Hamiltonian is just a boundary operator to translate back and relate to operators on the boundary at space-like separations from the underlying source. So that was supposed to be an argument for how holography, in fact, works. In fact, an even simpler version of that discussion or of that kind of story was given in this paper with Donnelly, where never mind propagation, you can just use the fact that the translation generators are boundary operators if you satisfy the constraints. And so you can take this state and translate it out to the boundary and observe it. And so in that sense, you can see, it looks like information regarding the state from afar. So specifically, this last example, you can take the address state and you can translate out to, say, infinity or to some distant point. Then you can measure and look at what you get, essentially. So it looks like at least information is localized differently in gravity, and it almost looks like it might be completely delocalized, and there's a question of how to think about that. Though there are some important notes and caveats on this story. So the first is that we really need to have a solution of the constraints for all of this to work. And moreover, in general, we need a non-perturbative solution of the constraints for this to work. And there's some more discussion of these questions in these two papers. Just to give one extreme example of why you need a non-perturbative solution for the full story. Well, if you think about, say, two different states inside a black hole, say maybe you have two different scalar fields and they're coupled to sources with the same profile, can you tell the difference between the state where you've created one scalar field or the other via this procedure? Well, so you can try to run this argument, but obviously you're going to need a non-perturbative solution of the constraints to convert or to explain the relationship of this state to the operators at infinity. Also, in addition, certainly when you're dealing with a non-perturbative gravitational field, in effect, like being inside a black hole. Also, you need to translate over a long distance, of course, basically out to infinity to make this work. And so that's another way of saying why just the leading order perturbative story is a bit of a challenge. Now, Lauda et al. Have argued that this story does extend to perturbative availability of information, say at infinity. But one issue is that in simple examples, the sort of signal of that information is exponentially small. And so it remains to be seen if that plays an important role. So in general, we need to take into account various limitations, and there is still a remaining question: in what sense is information effectively delocalized by these very important aspects of gravity? And in short, we can ask the question, are these effects sufficient to communicate information outside a black hole in a way that resolves the information problem? Or is some new non-perturbative structure needed? And I guess a different way of saying that is to say that, really, since the underlying story is we have to have a non-perturbative solution of the constraints to make all this work, that looks like we really need to solve the problem to sort of solve the problem, in a sense. We don't have an independent construction of the solution of the problem, say, just from holography until we've solved the constraints to begin with. At any rate, let's go back to our assumptions, and I've added now quantum mechanics to the list, and look at them some more and look at the possible ways that things could work. So one way of organizing those assumptions is to say that quantum mechanical evolution plus disappearance of the black hole at the end of evaporation imply that either one or two fail, or both. That's sort of a non-locality theorem. And we've discussed this question of whether there truly are subsystems with the kind of structure you need in gravity. But what if that is, in fact, the correct picture, that you can represent the state, say, in terms of subsystems, and to a good enough approximation that that doesn't solve the problem? So if that's the case, then you can organize this set of assumptions in a different way, that quantum mechanics plus subsystems plus disappearance imply that distinct black hole states don't have identical exterior evolution. And if that's the case, then you must have some kind of new interactions that go beyond local quantum field theory that in effect transfer information or communicate information from the black hole state to the exterior. You need black hole state dependent interactions. And that's a possibility I've been exploring in a series of papers going a ways back. And so I'll finish the time today by saying a few words about that. So the first statement is such black hole state dependent interactions violate semi-classical locality, as we've already explained, because we talked about how those were forbidden by the picture of local quantum field theory evolution on a background. But we can, for example, explore how those might work in a principled parametrization of ignorance. And in fact, this kind of approach can be quite powerful. In fact, there's one way of arriving at field theory, deriving field theory, by thinking of it as a principled parametrization of ignorance. So let's go ahead and try that here. In a brief overview is this paper here. So let's imagine that there is a suitable notion of at least an approximate division into subsystems of the state of a black hole and its environment. And the local quantum field theory evolution won't transfer information out. You need some additional contribution to the Hamiltonian that does so. And so the simplest form of determine the Hamiltonian that will do so is, well, some operator that acts on the black hole state. So let's take a basis of such operators, for example, and then times an operator that acts on the environment over here. So we have a coupling between the two. And of course, if we're thinking about all of this as, say, some small perturbation to the local quantum field theory picture, then we expect the environment, the state of the environment, to be at least approximately well described by local quantum field theory. So we might think we can build this operator that acts on the environment from local quantum field theory operators. And here I've just sort of described things on a simple kind of slice and sort of pictorially represented the fact that this coupling will effectively transfer information or entanglement from the black hole state to the exterior. Okay, so some other points on this kind of interaction. First, we need it to act on a scale at least out to the event horizon, we need the black hole state to influence things outside the event horizon. So it needs to act on a scale at least of order R. And you might expect that these operators act on a scale not just sharply ending at R plus L Planck, just a Planck distance outside the event horizon, but the natural scale is a scale of order, the event horizon size. Put differently, this is a way of avoiding this whole firewall behavior, which looks rather bizarre. You can think of that as arising from sort of an unnatural fine-tuning of the couplings of the black hole to the environment. So the natural scale is the event horizon size. And by the way, here we make contact with the earlier wormhole discussion. And also, that's really where, in a sense, the black hole radiation is produced, in a black hole atmosphere that isn't sharply at the horizon, but is a region of size of order the horizon length, distance around the horizon. So that's sort of where the problem arises, and you might think that that's where it could be solved as well. Another thing is that it seems like a reasonable hypothesis that the couplings here are universal to all different kinds of matter. Why is that? Well, that's the obvious way to maintain the very, or at least match onto some of the very nice properties of black hole thermodynamics. That's, of course, a very beautiful story, which we don't want to completely discard. Also, there are various Gedanken experiments involving black hole mining. You can construct thought experiments with different kinds of mining apparatus, or even threading a black hole with a cosmic string. You increase the rate of decay of the black hole, the rate energy comes out. You'd also like the rate of information transfer to go up at the same time. And then finally, there's just the universal property of gravity, which is suggestive of this. So we can satisfy those last statements with a more specific form for this interaction Hamiltonian, where we have a coupling between operators that act on the black hole state and the stress tensor to make things universal. and then integrate it against some things which you might call, well, form factor functions or whatever language you'd like to use. And these should be supported on scales of order the event horizon size. And we can then reorganize this expression if we combine or if we write operators that act on the black hole state in this form, including the form factors, we can reorganize this in a way that looks like a black hole state dependent metric perturbation coupled to the stress tensor. And so that's based on some pretty simple assumptions, the form of the coupling between the black hole states and the exterior. But what other constraints, this is still fairly general, what other constraints can be applied? And well, there's a very important one, and that is whatever these interactions are, they have a job to do. They have to undo the damage done by Hawking radiation, is one way of putting it, or they need to transfer information or entanglement at a rate of something like 1 qubit per light crossing time to undo that damage or to compete with the rate of entanglement buildup described by Hawking. So one way of achieving that is if the expectation value of this effective state-dependent metric perturbation is, say, of order 1 in a typical black hole state. That's sufficient. This will be time and space dependent on scales of order R, and that clearly is going to be able to affect the state and transfer information at a rate of order 1 qubit per light crossing time. So that's sufficient. That's actually looks like a rather big effect. We'll call this the stronger coherent scenario. If you really have something like a quantum metric perturbation that's of order 1, you might think that could have other impact on the exterior and possibly even be visible, say, to things like Event Horizon Telescope, because there we're studying light propagation in the vicinity of the horizon, or at least in the vicinity of the light orbit. And so that's a question, if this scenario, if this kind of scenario is realized, whether you could actually see some time-dependent distortion, say, in the images visible to Event Horizon Telescope. And that's something we've examined at some level, and really the fact that we have the images we have now, I think, in essence, place some bounds on this kind of scenario. But we can also ask what size of these interactions is actually necessary. And that relates to a very general problem, just in dealing with general systems with subsystems. If you have two subsystems, what is the rate of information transfer between the two, given certain assumptions, say, about something like thermalization in the subsystems and some couplings between them? And so in the present context, we can just estimate the rate using Fermi's golden rule, because if you have two systems that are coupled, then the rate that you transfer a bit of information is something like the rate at which one subsystem can emit a particle into the other subsystem or undergo a decay. So we'll use that kind of Fermi's golden rule estimate to estimate the information transfer rate. So we have the well-known density of final states times the matrix element of the perturbation of the Hamiltonian squared. And the interesting thing is that in the present context, the density of final states includes the density of black hole final states, which is big, say exponentially large, and something like the Bekenstein-Hawking entropy, say. And so if that's very big, then you can have rather small matrix elements of the perturbation Hamiltonian and still get an order 1 answer here. So those suffice. And so put differently, if a typical matrix element of this state-dependent metric perturbation is of order e to the minus the entropy over 2, that suffices. And this kind of scenario I'll refer to as a weak or incoherent scenario, in the obvious contrast with the earlier one. Now, of course, that's going to be harder to see with Event Horizon Telescope. You're not going to have a big effect, say, on light trajectories. But if you think about propagation of fields, say gravitational waves, in the context of including such an interaction, you are going to lead to an extra contribution to scattering of gravitational waves. And the scaling of that contribution has the same features I've just described, a large final state enhancement. And so you can have small matrix elements and get an order 1 result. So you can get order 1 corrections to gravitational wave scattering, say at wavelengths of order r, from just this kind of simple estimate. So in other words, possible modification to absorption or reflection of gravitational waves from black holes. And so that's something that we're actually able to observationally study. That's what LIGO and Virgo are doing. They, part of the signal is in the regime of gravitational waves, sort of comparable in size to the black hole horizon. And so there's the possibility of observational consequences there, which is still being explored. Okay, so that's a brief summary of this essential story. And I'll just end the talk with that and give an overall summary. So first, I've organized things by saying that we have this set of postulates or assumptions, the validity of quantum mechanics, and in particular, unitary evolution. The black hole is a subsystem. Distinct black hole states have identical exterior evolution, and black holes disappear at the end of that evolution. And those 4 statements are inconsistent. And a helpful way of thinking about things, at least in my mind, is to understand how a given scenario evades that and how much extra machinery you have to introduce and what it means, what it's telling you when you have a particular way of, say, stating that you have a loophole to this. In particular, the question of subsystems and gravity, in my mind, is a very important one. How to think about subsystems. It seems like that is likely part of the basic structure of quantum gravity that we haven't really properly understood at this stage, or at least not completely understood. We have some results, but there are some remaining puzzles. And then finally, there are different ways of organizing this statement of inconsistency, but one way of organizing it is to state a theorem that if you have quantum mechanical evolution, an effective description of subsystems, and black holes disappear at the end, then there do need to be new interactions between the black hole internal state and the black hole surroundings. Those are non-local, of course, with respect to a semi-classical description, but we can give a parametrization of them. And they lead to possible observational consequences, for example, with Event Horizon Telescope or gravitational wave detection observations. So I'll stop there and take any further questions. Thank you.
Okay, thank you very much for your very interesting, for great talk, in fact. So question, please. Igor Ivanovich, please.
Thank you very much, Steve, for a nice but very clearly given talk. I have such question. When you speak about disappearance of black holes, do you mean literally it disappears, or maybe stop at the Planck length?
Yeah, I do mean literally disappearance, and I encoded that in the way I stated the postulates. I guess I could try to go back, but in the statement that, or let's contrast 2 things. So one possibility is that the black hole evaporates, and then, in the future, say if you look at the asymptotics, there's, no Planck scale remnant, no nothing. There's just outgoing, say, Hawking radiation. So that's disappearance, and that's the thing that seems to violate unitary evolution of quantum mechanics. And we can contrast that with scenarios where the black hole evaporates down to the Planck size and then leaves behind something that is of Planck size, say has a Planck mass and has some internal states. So that's the other possibility of not disappearing. And that kind of microscopic remnant scenario is the type of scenario that there have been many arguments causes extreme trouble, because you have this spectrum in your theory, which corresponds to having these, Planck mass objects, but with an in principle infinite number of internal states. And those tend to behave badly when you think about their production in other contexts.
So your favorite scenario is complete evaporation.
Well, I think that if the alternative is a Planck size remnant or let's just call it microscopic remnant scenario. And that alternative looks to me like it's essentially ruled out unless there's some little tiny loophole we haven't found, but there's fairly general reasoning that that's ruled out. I guess the other alternative is you have complete disappearance and you just violate quantum mechanics. But
there is an obvious problem with complete evaporation because the Hawking temperature is inverse proportional to the mass, and at the end we have an explosion.
Yeah, it does go quite rapid at the end, and yeah, that's something that's been discussed, and actually, of course, is of interest potentially to astrophysicists because those end stages, you could ask if they're explosive enough that you could observe a primordial black hole decaying at some distance.
Thank you.
Mm-hmm.
More questions, please? Oleg Teryaev, please ask your question.
I have a question concerning time irreversibility. The classical black hole formation and Hawking radiation are time irreversible. Would it mean that restoring the unitary evolution automatically produce a reversible picture?
Yeah, I think, well, first there are different levels to address that question. Let me see if I can go back. Sorry for the slow scrolling. This will do it. So at the level of thinking about the quantum state evolving from this slice to this slice, in fact, you do have reversibility, but that's just the quantum field theory perturbations on a background. And the problem is that if you have evolution like this and then say the black hole disappears, one way of stating what's wrong with that is it's not reversible. And that's associated with the violation of unitary evolution. And so, yes, it seems that if one is able to find an explanation of how you have unitary evolution, that looks like it should go hand in hand with restoration of a description that is reversible as well.
No. As unitary evolution is always reversible, right? Yeah.
I think in any reasonable context.
Okay, thanks.
Okay, more questions, please? We can wait.
I was expecting more controversy. Usually there is.
Andrei Barvinsky, Andrei, please ask your question.
Well, yes. Hello again.
Hi.
Do you hear me?
Yes.
Yes.
Okay, very good. Let me ask such a question. It would seem that basically, well, in the last couple of years, I got used to the idea that there was a great breakthrough in the understanding of the problem of information loss, black hole information loss. And it's interesting that this understanding came through the ideas of, I'm afraid that I just missed the beginning of your talk, Steve, but in the end, it would seem that this stage curve reasoning was actually substantiated by entirely semi-classical arguments, including the selection of a useful 7 point in the corresponding path integral and so on. But it would seem that what you suggest now that there is no real understanding in this sense, and you say that actually semi-classical argumentation does not work at all. So what would you say about this?
Well, that's maybe a bit of a strong rephrasing of what I said, but yeah, okay. So there has been obviously a lot of interest and activity in the story of replica wormholes. I've been trying to understand what it really says at the level of states and amplitudes. And I think others have as well. And, there is this prescription for, finding these different saddle points and gluing them together, or, having a transition between them that, that gives a way of reproducing these curves, both of which we knew before. And so it's just telling you how you transition from one to the other. So there's an interesting story there, but I think it is still limited because we haven't understood how it fits into this language of states and amplitudes and so on. Again, the possible connection to baby universe emission is interesting as well, but there are some questions which I've raised there, which I haven't understood the answer to. And maybe some of the experts who have been, thinking even more about replica wormholes could explain, more in this way of thinking about things, what really is going on. But to me, it looks like we're still missing some important ingredients in the explanation.
Well, if I actually would formulate your suggestion in such a way, would you agree with that? So what you suggest for me, it seems that what you suggest is the following, that in order to construct a clear picture, you have to introduce the notion, and actually not just introduce the notion, but just define, calculate, gauge invariant observables, gauge invariant in the sense of diffeomorphism invariants, which are of course non-local, almost non-local, because of the non-trivial structure of diffeomorphism transformations touching also the coordinates, space-time coordinates of the system. And since because of this non-locality, you have to reconsider the problem of separation of the system into subsystems, and when one of the subsystems is identified as a black hole. So is it actually basically the main problem is some perturbative or non-perturbative construction of gauge invariant observables in quantum gravity? Is it right? Or you mean something more than that?
Okay, well, let's back up. So first there's the question of the replica wormhole story, and I think to make that, say, more complete, we'd like to know how to compute more than just entropy curves. We'd like to know how to compute some set of quantum amplitudes and so on, between representing transitions between states or whatever, which give a more complete picture. Now, those amplitudes, just thinking generally in quantum gravity, you can describe different kinds of amplitudes you might want to look at. You might want to look at things that are more S matrix-like, or you might want to look at, say, expectation values of observables. And so just generally in quantum gravity, the question of how to think about observables is an important one, and it ties to this underlying question of the structure of the theory. And so that's where I've made more general comments, not necessarily pertaining to the replica wormhole story, but just more general comments that we would like to understand the underlying structure of gravity, and in particular, how to think about division of things into subsystems. And so studying the observables is one way of attacking that problem. And I've pointed out that when you do so, you have some results that from some perspectives look surprising in comparison with local quantum field theory. So I think a better understanding of observables may go hand in hand with an understanding of this underlying structure of how to break things up into quantum subsystems. I'm not sure if that quite answers your question, but I hope it gets at some of the important features of it.
So the problem of dressing, or the solution of the problem of gauge invariant observables in terms of gravitational dressing is just a minor part of the whole problematics here.
Yeah, that's just the perturbative dressing is just a start. It's the beginning of a story that we'd like to complete, I think.
Okay, thank you. Thank you very much.
Okay. More questions, please?
Hi, yes, can I have a small question?
Yes, please.
At the beginning of your talk, you mentioned the notion of quantum atmosphere around the black hole. I was wondering if that would change or it would have any role in this story at all.
Well, so first of all, I've argued elsewhere that really we might want to think of the Hawking radiation itself, just in the Hawking process, just in the local quantum field theory description, is being produced in a quantum atmosphere that has a thickness, say, comparable to roughly to the thermal wavelength, or to, in the case of higher dimensional, 4 and higher dimensional black holes, comparable to the horizon radius size around the horizon. And specifically that the Hawking radiation, maybe in some basis dependent sense, you can think of it as produced, down at small distances from the horizon, but really it's more natural to think of it as produced in this quantum atmosphere, which has a thickness of order of the horizon radius. So that, I've argued, is the story in local quantum field theory. And then when we look at whatever the completion of that is, involving the full story of quantum gravity that restores unitarity, you might think that the effects that are important could be relevant also in the full quantum atmosphere region, rather than just being relevant, say, a microscopic distance outside the black hole horizon. So that's one of the things that's come into the set of assumptions I've explored when thinking about parametrizing new interactions between the black hole internal state and the environment of a black hole.
Okay, thank you.
More yes, Raman, please ask your question. Yes.
Hi, Stu.
Hi.
Thanks for the nice talk. I want to understand your concept of subsystem. Well, if you, according to your talk, if you have just a single black hole and some environment, then I understand, like you are treating this whole black hole, whatever inside is a subsystem, kind of, right? Then how do you describe, for example, if you have two black holes kind of in the process of merger? I am not asking after the merger there is some resultant black hole, but in the process there are two subsystems kind of interacting very gravitationally, so high gravitational effects. And maybe, I don't know, in that situation you may have to consider back reaction as well, because there will always be particles falling into the whatever, even during the merger, right? So
yeah, so let's organize that question in a couple of different ways. So first of all, just in local quantum field theory, we have things like mergers of subsystems. So let's just think about good old field theory. I can have a subsystem corresponding to excitations over here and excitations over here, and then I let those evolve for a while, and the excitations can get mixed up into, say, some bigger subsystem up here. All of that without gravity, that's just true. So you can have different organizations of what you mean by subsystem. And so you might think if you have a local quantum field theory description that's pertinent to black holes, you could just say the same thing where what I just described is applying to black holes. But then, of course, once you include the effects of gravity, the whole discussion of how to think of even one black hole as a localized subsystem is at least modified, and we need to better understand, how we should be describing that as a subsystem. And if indeed there is some effective delocalization of the information, maybe at the non-perturbative level, which we're still grappling with, then maybe this black hole over here isn't really an independent subsystem, or at least we've got to figure out in what sense it is. So there's a new set of questions at the gravitational level. And of course, when they merge, then, well, you've still got the same set of questions to address at the level of the bigger black hole later.
Okay. And what about the back reaction effects, gravitational back reactions? So do you have to consider them when you are dealing with these two subsystems which are in the process of merging?
Yeah, I think, the gravitational dressing, or even let's think about the, we could think of this picture in the context of, say, two black holes, and the leading order dressing of this one is sort of its leading order gravitational back reaction on the external state, likewise for this one. And of course, when you bring them into the same vicinity, they're going to be interaction terms, so to speak, as well, and so on. So you have nonlinear effects in the dressing as well with sort of two such systems. And yeah, so in general, dressing is a way of sort of describing the effects of the gravitational back reaction. Is one way of putting it. Describing the dressing is, describing the results of the gravitational back reaction.
Okay.
Okay.
In this picture, these operators O, J1, J2, commutator is non-zero, then, I mean, it's equal to what?
That's an interesting question. You can actually, and we did that in this paper, you can ask what size are the corrections to the commutators, and they're typically proportional to things like gravitational potentials in 4 dimensions, GM over R. So there are things that become large when you have situations that are, creating effectively a large gravitational field, something like forming a black hole when GM over R is of order 1. That's sort of the typical parameter for how big these things are.
Okay. Maybe the last question, I guess, if there are more questions, please. Okay. If not, let's thank Steve once again for his great talk. It was very instructive. So thank you very much. We will think more about all this stuff. Okay, thank you. Thank you, Steve.
Thank you very much.
Thank you. I appreciate it.
Thank you.
Thank you.
Thank you.